And obviously, recording will be posted, notes will be posted. I'll try to post them as soon as possible. I'm just a little busy with finals as well, but I'll be timely. Otherwise, let's get right into it. And in the middle, after doing 18 questions, I take a short 5-minute break just because I realized that my legs are not built for sitting down for 3 hours straight. So yeah, let me go get a drink first. Hold on. All right. First question. Consider the following sinusoidal steady state circuit with 6 ohm resistor and a 3 Henry inductor. If x of t is the input signal and y of t is the output signal, what is the frequency response of h of omega of the circuit when omega equals 2? So obviously you could do this in two different ways. I will do the standard way where I'll just find the transfer function. So first of all we know for a fact that the transfer function is equal to this. And especially for RLC circuits, we know that they're LTI systems. And so this LTI system will yield the fact that we have that the output signal will be, how do I want to put this? J omega L over R plus J omega L times X omega. Because we know that the output, let me actually elaborate the output first. We know that the output corresponds to this. Therefore, this ratio must just be this fraction right here given straight to us. And so now all we need to do is just kind of plug in the numbers that are given to us. And so we will do so. Let me turn on the chat too, just so I could see it. And so now we know that omega equals 2 and L equals 3. And so we get that the numerator is 6J. The denominator is 6 plus 6J. And so this is 1 over 1 plus J. Hold on. Yeah, we're fine. 1 over 1 plus J. Then this is 1 over 1 minus J over 2. Hold on. Oh, no, sorry. So I could multiply top and bottom by 1 minus J over 2. And then I get... Okay, that's already weird. I think hold on. 1 J over J omega L, R plus J omega L. Well, what?
There's a J on the top.
Wait, hold on. I'm very sorry. The numerator should be J. Sorry about that. Yeah. Oops. What in the world it's first question already and I'm messing up. Yeah. And then I can multiply top and bottom by J, so I get 1 plus J over 2. There we go. Yeah, I don't know I guess I'm already rusty from this. It's been a week. All right, anyways, hopefully if there's any questions. Yeah, this is gonna be recorded. All right, so there's no question. I'm gonna keep moving. But again, please feel free to interrupt through the mic because I would like to just hear you. If f of t is given right there and g of n, if g of n are the exponential form of the Fourier series coefficient of g of t of f of t, g of t, which is a derivative of f of t, then what is g2? And so, first of all, it's kind of important to recognize that this kind of expression describes I mean, you'll learn in 101, but it's called the analytic form of, like the analytic equation of the Fourier series, where you are always representing your periodic signal as a sum of complex exponentials. And so knowing this, we could decompose our f of t into the following. 1 over 1 plus n squared e to the 3j and t. And so from this, we could recover two things. We could observe that f of n, the Fourier series coefficients are 1 plus n squared, and omega naught is equal to 3. Okay? And secondly, um, one of the main things that this question is particularly asking is that if g of t is equal to the derivative of f of t, then the Fourier transform will have a very particular form that correlates to the Fourier transform of f of t. And so now the question is, what is that? Well, we know that the Fourier transform pair of f of t, of the derivative of f of t, is exactly j omega f omega. And as a very simple, like if you really want to see it very simply, we know that this is true. Oh, sorry. This is not Fourier series. Has Fourier series. J omega naught Fn. As in like the Fourier series coefficients of f of t will have the Fourier series coefficients of f of n multiplied by j omega. J omega Jn omega naught Fn. And why is this true? It's important to ask, why is this true? Um, of course, I'm sure you have seen the property that like this is known. This is something you know. Like this is actually very similar to what the Fourier transform version is. This is the F transform version. And the of course, you could actually just end off this and conclude that your final answer is just equal to Gn. And so G2 will be 2j, so 6j times 1 over 5. So 6j over 5. You could just conclude like this, of course. That's it. Like that's fine. That's completely fine. But I feel like it's important to understand where this kind of relationship comes from. And so I'll just do a very quick summary of where it comes from. And so we know by the analytic equation or the inverse Fourier transform equation that f of t is equal to the a sum of complex exponentials. And there's a very nice property that you could push in, like the derivative operator is linear. And so this is equal to the sum of the derivatives. Of course, this is only well-defined if each of these terms are differentiable and like it's well-defined, as in like it doesn't just blow up to infinity immediately. And so given that our function is kind of nice, we could push in dt into the sum so that we get dt fn e to the j omega naught, and realize that that's a constant, that's exponential, and so we could just pull out everything up top and obtain jn omega naught fn e to the jn omega naught t, and we have recovered our gn. Maybe I'm gonna draw it all the way up. That's where it comes from. So it's just kind of just nice to see where these operations come from, but you know, the answer remains the same. Is it the same as the trigonometric form? Yes. In fact, a lot like as in like if you're talking about the trigonometric form, we're saying like, oh, it's equal to a cosine omega naught and omega naught plus bj sine omega naught. I think that's what you mean. And yeah, it's the same form because the complex exponential is exactly that. But the main issue, the main reason why we don't use that form is because it's just more notation. And it conveys the same value, like it conveys the same information. And so I feel like there's no real point writing all that stuff. You just write complex exponential and it's convenient. But of course, when you're doing like real signal analysis, then like real signal analysis, as in like your signal is a real function, then of course observing the cosine part is very convenient. Anyways, moving on. Suppose the output of an LTA system is that when the input is that. What is the output for the same system when the input is, oh, okay. So, huh. Um, well, let me draw a diagram first. So we know that for an LTA system, if we put in any e to the j n t, j omega t, then out comes h omega, which is a constant, e to the j omega t. This is LTA system. This is the eigenfunction property. And so what this means is that when you put in 2j e to the jt, 3jt, then we must obtain e to the 3jt because these have to match with each other. Remember, it's an eigenfunction property. Essentially, I'm saying if I give you a vector in this direction and I put it into this LTA system, linear system, then what I obtain on the outside should face in the same direction. It could be scaled up or scaled down, but it must face the same direction. And so given this idea of the eigenfunction property, we could correlate each of the terms in the input to a particular output. This is enforced. This is enforced. And so given this, we could observe that 2j e to the 3jt is equal to negative e to the 3jt, h omega, it should be particular, h of 3 e to the 3jt. And this must mean that h of 3 is equal to 2j. Similarly, we observe that e to the negative 2jt must be equal to e to the h of 2, negative 2 times 2 e to the negative 2jt. Then we observe that h of negative 2, sorry. I messed up there. Oh, no, I messed up there. There we go. Sorry about that. My input-output relationship. So negative e to the 3jt divided by 2j. I don't know how I want to do this. Here, let me put it this way. Okay. H omega is equal to, sorry. So this is omega equals 3, and this is omega equals negative 2. And so h of 3 must be equal to my output divided by input. This is by law. Like that, this is all enforced by the eigenfunction property. And so we obtain that h of 3 is equal to 1 over 2j, negative 1 over 2j.
Excuse me.
Yeah.
I think you got the input and outputs flipped.
Oh my God. Thank you. I'll just switch the direction of the arrows. Nice catch. What the heck? I need to work on my reading today. Oh, that actually makes the thing much simpler. Then we get that the input-output relationship for omega equals 3 is just 2j, negative 2j. That's nice. And the input-output relationship for negative 2 is equal to e to the negative 2j t divided by this, which is equal to 1/2. And so what this means is that if I input this, then I must obtain h of 3 2 e to the 3jt plus minus h of negative 2 j e to the negative 2jt. Is this clear so far? So essentially, all I use is the eigenfunction property to find out about these two. And then I'm just considering the LTI system output for a sum of terms, which is pretty straightforward. And so
Oh,
now,
oh, I was gonna ask, uh, will there ever be a scenario where the output will be a different frequency? Like maybe instead of the exponent staying as like that same polarity, like it switches?
yeah, that's possible. Consider the following. If I give you cosine of t, and then like it's very funny how this works, but if I say I give you negative cosine of t, technically speaking, I could like this is the same as wait, no, sine, sorry, I need to think of sine. If I give you sine and then I flip it, then this is the exact same as cosine of negative t. And so technically speaking, I kind of flipped the frequency, right? And so um like from a stylistic standpoint, like technically speaking, if you look at this, um technically no, but mathematically yes. I'll put it that way. And so it's not that the delta function at one, like if I in the example that I particularly gave you, where I gave you sine of t, and then, or I mean, hmm, I feel like it's better if I just give you a complex exponential. Let's say I give you e to the jt, and hmm, will the frequency ever change? No. Actually, never mind. Yeah, the frequency will never really change. Yeah,
So linearity would only affect the like the front coefficient.
correct. That's the exact point of the eigenfunction property, is that the complex exponential component doesn't change. It's like an eigenvector where it's like the part that stays consistent. Because it's like I have a function that sends this thing right here. So if this is my input function, then ff sends this function to another function, let's say y of t. But I'm just saying that the frequency of these two must stay the same. Uh, because, oh, okay, wait, sorry. Let me clarify from the top. The eigenfunction property states that if I apply this linear operation, that LTI system, then all that happens is the direction of the function doesn't stays the same, but all there is like there's an extra coefficient. So yeah, exactly what I said is, and exactly what you said is, all you do is add a constant. The complex exponential will not change. Never. Unless you're multiplying by zero, but that's a different story. Does that like reaffirm your assumption?
Yeah. I
Okay.
was a little confused because I think in a previous exam, I could be completely wrong and I'm just recalling wrong, but there was one where they gave us a negative complex exponent, like the exponent was negative in the complex number, and then the output was positive. Um,
Oh, there was that one. That was because uh oh no, I feel like you're talking about the one where it's like this, where you figure out you try to figure out this by relating some output input output relationship. So you figure out this, and then you also have the assumption such that h of t, the impulse response, is real and even. This means that you have this relationship, and so you would use, and then on your final answer, you use the positive part. I think that's the one you're talking about.
oh, I see. Yeah. So it would just be switching the polarity.
Yeah, essentially you would just be switching like the sign of the frequency by using a property that the impulse response is real and even. But otherwise, um, but otherwise, that's a little disjoint just because like you're not dealing with the input output relationship itself, but you're kind of figuring out the another value of the frequency response. But for this particular question, and even in general, this always holds. This is very important. Let me just start that. And so what we obtain is, now we just need to evaluate it. This is negative 2j, so this is negative 4j e to the 3jt minus 1/2 j e to the negative 2jt. And so that should be an answer for that. Voila. Okay, I'll move on. Consider the cascade of two LTA systems shown below, the input x of t and output y of t. If the impulse response of each of these LTA systems is a rect function, then what is the output y of t when the impulse is delta of t? So first of all, we know that this is delta of t. And this immediately tells me that the output right here is just h of t. Why is that? Well, delta of t inputted into any LTA system with impulse response gives you just the h of t, the impulse response. And so all we need to do, it means that y of t is equal to h of t convolved with h of t with itself. And you can do a bunch of things here. Like now here you're realizing that you're convolving two rect functions. And so you have to do it in time. There's no other way to do this. And so I guess I will do it. So let's get right into it. This is also equal to the integral h of t, h of tau, h of t minus tau, d tau. And then let's actually draw out our nice little rectangle here. Boom, boom. Okay, that's our anchor. This is tau. And so now all we need to do is figure out what our overlap looks like. And so actually, I found out a new way to kind of show time convolution in a nice way. And so I will actually try that idea. And so hopefully my lines line up like this. And then I will do the following. Consider at this -1 point, actually, I'll do this. So consider anywhere on these points. If you have if you have the rectangle centered at any of those points, let me actually highlight over here as well. There we go. Then what does it mean? That's a very, very bad yellow, so I will. This just means that there is no overlap between the two, the red rectangle and the blue rectangle for t, either t less than -1 or t greater than 1. Does everyone see this? So if we have t in these ranges, then we realize that there is no overlap between the orange square and the blue and the red square. And what does this mean? This implies that the integral of the rect function h of tau and the translated rect function must be equal to 0. So this is very important here. I want everyone to know like where I'm doing all these convolutions. If I'm multiplying, like if I'm multiplying two rect functions such that there's no overlap between them, then the orange function is 0 when the rect function is not 0. And when the rect function is 0, the orange function can be non-zero. And so everywhere, no matter what, the product will just be 0. And so since you're integrating over a product, a thing that's just 0, you get that everything is just 0. And so what happens is that our plot looks like this on all of those points outside. Let me actually make my thing thicker. Make it 26. Okay. Now let's look at the next point. Oh, wait, wow. I drew that, not draw that to scale. There we go. There we go. Perfect. And so now let's take a look at other points. There we go. Let's take a look at other points. Consider placing the box somewhere in this region. Maybe like right here. Then, so I'm going to highlight this part in blue. This part. I'll just highlight it all blue. Then we have some sense of overlap, like partial overlap. You put this box anywhere you want, maybe even like right here. Then the overlap kind of exists, like there exists an overlap. And so starting from this point to here, the overlap increases. Imagine literally just moving the square over the red rectangle, and the overlap slowly increases. And then as you move the blue rectangle, as you move the blue rectangle to the right, or as t gets bigger, the overlap decreases. And lastly, it will peak. Everything will peak when there is exactly an overlap at t equals 0. At t equals 0, it should be 1. Like, as in, if t is between 1 and 0, then it's increasing, then overlap increase. If t is greater than 0 and goes to, that's the wrong number, then the overlap decreases. Remember, this is all as t increases. And lastly, if t equals 0, then we have peaked, like peak. And the overlap is exactly just, it would just be h of tau times h of tau integral, which is literally just, literally just the direct function itself, which is just 1. And so it'll peak over here. And now you just connect all the dots with purple. I will do it in purple. I'm going to call those 26. Boom, boom. And there we go. And there's our answer. And yes, you could actually do this completely algebraically. Well, that is way too thick. And yes, you could do this completely algebraically if you want. But like, and yes, me drawing this out took a lot of time, but I will kid you not that if you get a gist of how this visual convolution works, then this will not convolving these two functions will not even take you like a minute. What goes on in my head is I'll literally, like when I first saw the question, I was like, oh, I'll do that. I'm like, oh, okay, I'm convolving two rect functions that are unit squares. I place a unit square, and then I place another unit square right here, and I center it at t. This is over tau, obviously. This is tau equals t. And all I do is I'm like, okay, my overlap, or the integral of the overlap is 0, 0, 0, 0, 0, 0. Oh, it's increasing. Oh, it peaked here, and it should be 1 because it's just overlapping unit squares. And then decreasing, and then 0, 0, 0, 0, 0. I'm like, oh, so it must be a linear function up, 0, 0, 0, linear function up, peak at 1, linear function down, and then 0 again. And that's it. That's the first thing that shot through my head when I saw the convolution of two rect functions. Technically, you can memorize it because this kind of convolution is kind of like prominent, but it's good to know how to convolve efficiently because you will be using whatever this technique that you learn here in for future classes. That took way too long, but this is important. Convolving like two functions in time is very important. But who knows? It might not even be tested at all, but it's a good skill to have because it helps how to think. Otherwise, we'll keep moving if there's no questions. Two periods of a periodic function x of t are drawn below. If x of t is the input to an LTI system with frequency response h of omega, where h of omega equals 2 if, okay, and 0 otherwise, then what is the output y of t? So we observe that the x of t is a periodic function. Oh, that's red. X of t is equal to some xn e to the jn omega naught, but clearly this is a period 3 function, which means that omega naught is equal to 2 pi over 3. Jn 2 pi over 3t. And what this means, and then of course x of n are unknown. What this means is that this yields a Fourier transform that is an impulse train. And hopefully I'm doing this correctly, but oh, wait, hold on. It should be 2 pi times xn delta of omega minus omega naught n. I believe this is right. And of course, to this day, even after this conversion, we still don't know what x of n are. But that's okay, because let's actually consider drawing out the spectrum of x of omega. We have an impulse center at 1, and then we have an impulse center at 2 pi over 3. Four pi over 3, so on and so forth. And what happens is that we're multiplying this to a LTI system with frequency response of that. So we want y of omega, which is equal to h of omega times x of omega. And so now let's try drawing out h of omega. It is 0 everywhere else, and it's only 2 between 2 to 4. Where is 2 to 4? Where is 2.5 to 4? Well, 2 pi over 3 is approximately 2, or it's a little greater than 2. And 4 pi over 3 is a little less than 4. And so what happens is that we realize that h of omega actually lives exactly between two impulses. And it's 0 everywhere else. And so what this means is that because h of omega has 0 overlap with x of omega, we have that this is just equal to 0. And thus, we get that our answer is evident. This is 0. Okay. Next question. Consider the system shown below. For what values of A is a system linear and time invariant? Okay. So this is very interesting. There's actually a question on this on Piazza, and it's a great time to kind of think about how, kind of revisit this old topic. So let me put it this way. There's multiple ways to analyze this. Obviously you can do it algebraically, but the easiest way to make a counterexample of something is to just, the best way to disprove something is just by a counterexample. And so let's say you pick any arbitrary A. So let Like pick any A. Let's play a game. It's essentially making a counterexample is like a game where a game master tells you pick any A. And sorry. You tell someone pick any A, any real number you want. And then after they give you the number, you will craft an example that disobeys the statement. And so let's take a look. Let's take a look here. What was it? First of all, kind of like a trick question, but actually, let me do this first. The system is linear. It's very clear, mainly because we know that uh, if x of t yields y1 of t, and x2t yields y2t, then x1t, okay, sorry. I would really like to be coherent on the notes, so let me just write it all out. Boom. Then x1t plus x2t, it will yield you the integral from a to t of x1t plus x2t tau, tau. Let me make sure that's all tau. And this is equal to, well, the integral operator is linear. And so you can break this up into two. And then we realize this is just the sum of the inputs, sum of the outputs. And so clearly it is linear. But now the only issue is time invariance. Shouldn't we add constants A and B to show, yeah, that's a good point. Let alpha and beta be real numbers. There we go. Thank you very much. Let alpha and beta be real. Actually, they can be complex. I forgot. Okay. Now, here's an important part. Is it time invariant? And now I'll show you why it's not time invariant. Let me draw a graph. So essentially what you're doing by doing this function is that you're basically picking a particular point, any arbitrary point, and you are basically saying, evaluate this integral, like, how do I put it? As t goes on, you're basically, for any particular t, you're basically saying, give me the area between it, like within this part. And like, yeah, I think that's pretty self-explanatory from the description. And so I will think of any particular counterexample. Hold on, I need to think of one though. Just think. Okay. Consider this particular example where I give you hold on. I give you an A. Let's say without loss of generality, A is just 0. So A is just 0. Then what happens? And I say, what do I say? And that's causality. I say, I'm going to give you an input such that it's going to look like this. Just a unit step function. I'm pretty sure this is going to work. then very clearly we understand that the hold on. If I pull it back, if I pull it back, then it's going to look the same probably. Let me change it. Let me say I'm going to just give you something else. Let's say I give you the linear function. Then what happens? Um, then so x of t is equal to x of t is equal to t. Then my output is equal to two different things. Sorry, let me do this. If t is less than, so because of piecewise function, if t is less than 0, then we get two different things. Integral from, sorry, integral from less than 0, that's 0 to t of t squared, 1/2 t squared from 0 to t, sorry, that's just 1/2 t squared. And then, oh, maybe that's actually the same. Hold on. Huh. Wait, I think it's actually the same regardless. I think it's just 1/2 t squared. And then, yeah, I believe, never mind. This example doesn't work in particular. Let me actually think about this. Ah, time invariant. Roche values of A. If I give you any A, then if I shift it, it's mm,
I have a question.
yes.
So basically, is it not time invariant because we have an integral, or is it we're integrating, or is it because we're picking all the options in this question is just an arbitrary point? So anything past or before that point will make the output change. Like, because I was
Mhm.
thinking, my thought process was, what if A was negative infinity? So it we're picking it from like it doesn't change within all time. So then it's not a set value. So would that make it time invariant, or am I on the wrong track in that?
So the main way that I look at this is that for any, so first of all, my first initial observation is that if you pick any finite value, then okay, how do I put this? If I say, if I find you a counterexample for 1, for a equals 1, then I also have a counterexample for any other finite number. Because if you give me -1, then all I can do is move my counterexample over here and it should work the same. Because integrals are translation invariant. Now the thing is, so basically my first observation is that if I find a counterexample for for any finite a, yeah, that's a, then I have a counterexample for all other a. Okay? Just because like I could just move over my counterexample and then it will operate the exact same way. So now what happens is that for the negative infinity case, let me think about it. I mean, under assumption, I believe it is still I would have to think about that. I would have to think about that. But we're just working with all the answer choices we have now. And so I hope that my point is clear is that if I find a counterexample for one particular number, then I have a counterexample for every other number. Is t finite? Given these answer choices, yes. Like we're working with the answer choices of what we have here. It may be
So
or t equals infinity or negative infinity, but it's just that that's not that's not given as a number. And so yeah, again, back to simplicity, I'll actually assume that a equals 0. Then our system is x of t given to the system, and we're given a to 0 to t for t 0. Okay? And I think I have it. Let me just make sure it's right. I think so. Yeah, it's right. Okay. And my counterexample is actually the one that the one I actually stated in the beginning is just a unit step function, which is like kind of like the most basic example. And so let's actually see why. Or I believe it works. Let's actually just try it out. It's just a test function I just thought of. If I put this into the system, then what we obtain is that it is if t is negative, then it's just 0 because you're integrating over just nothing. Like if t is negative, then you're integrating over all this, which is just 0, which is very simple. And if t is positive, then your output function is t. Now consider shoving in a function that is translated by just to the left by 1, to the right by 1. Then what happens? Well, I prefer to actually just uh, draw it out first. I'll draw it to scale actually. There we go. And so what now? Well, now what happens now? Well, if t is less than 1, sorry, if t is less than 0, if t is less than -1, then you're actually taking a normal integral. Like you're taking an integral of all this. So you'd be taking an integral -0 to -1 of, sorry, 0 to -0 to t of x of t, u of t plus 1 d tau. Let me clarify that. And then you have something down here. And you don't even have to like finish the other cases. You just need to evaluate this. And so let's evaluate this integral. Well, it is just, you realize that for any tau less than -1, you have that it's just like u of t plus 1. This is just 0. Like for any point beyond here, u of t plus 1 is just 0. So we could just constrict this bound, this integral bound from 0 to -1. D tau. And then lastly, we realize that this integral is actually very easy to solve. It is simply just -1. Let me just make sure that's right. Yeah. And so what happened here? Well, when we put the unit step function into our system, what we expected is a output that looks somewhat like this. And linear LTI says if LTI says that what we want is if you have a shifted input to the left, then this is our expected. This is our time invariance expected. Ti expectation. That's our expectation if Ti is if the system is time invariant. However, what happens is that if you do actually shift it, then we get that the integral of like the values beyond some point are just -1. And from this point, like it doesn't matter what goes along beyond this point, you're already done because now that the output of u of t plus 1 is -1 at all these points, it will never be equal to the time invariant expectation. And so now these two will never be equal. So again, a general rule of thumb is to prove time invariance, you do two things. You obtain expected, sorry. Assume time invariance and obtain output. And that's this part right here, where time invariance said if I shift the output to the left, then if I shift the input to the left, then the output must be shifted to the left. That's time invariance. And so that's my assumption. However, and then all you do is check if shifted signal matches. It matches the expectation. And that will prove time invariance. And now the next question is, how did I come up with this counterexample? It mainly lies in the fact that it comes from looking for a sense where you have a constant. I'll explain what I mean by that. Let me actually elaborate. And okay, I guess this officers will take a while, but let me go add an extra page because it's actually very interesting. Add a page after. My main concern lied in the fact that it relied on a constant here from A to T. This was rather, like the only thing that miffed me was this, because these kinds of constants where you're looking at a fixed time, like how do I put it? This is literally a fixed time. As in you on your graph, if you have a set amount of time, you're kind of always looking at this one particular point, t equals A. And then you're integrating whether like this way or that way or whatever. And these kinds of nuances where the equation kind of focuses on one particular moment of time, that usually implies that it is not time invariant. Input is shifted, the upper bound is shifted. Like, yeah, exactly. Like, okay, well, like obviously you can definitely do things where yeah. Yeah. You can do that kind of thing. But in general, when you see these kind of like when you see this kind of value or this particular portion of the equation that fixates, that's the word, it fixates on one particular section of time, then that usually implies that it is not time invariant. Let me give you an example. For example, like your classic examples like, oh, x of absolute value of t, well, definitely not time invariant. Or oh, x of t squared, like somehow it messes with time. Let me just think of another non-trivial example. Hmm. Uh, maybe it's not easy to make too many examples. Integrals. Integrals have a tendency to be a little, just little weird. I think this should be not time invariant. Let me think about this. Hold hold on. I'm doing this, I'm checking the integral. No, yeah, this is time invariant. This is no, this is not time. Is this time invariant? Yeah, that is time invariant. Any integral where, like, again, like this particular equation, like if you're taking the integral from like some a constant to just another constant of x of t, x of tau d tau, like all of these where you're fixating on a particular time point, you could kind of suspect not time invariance. How does integral ut plus 1 equal -1? Okay. So this is equal to 1 d tau, and then this is just tau evaluated from 0 to -1, which is just -1. Like because in this interval right here, this is the interval you're thinking of the interval -1 to 0, and in this interval you have tau plus 1 evaluates to 1 in these points. But if infinity and negative infinity was a choice, it would be, since it's not a fixated point. Let me think about that. Let me think about that. This is a complete disjoint, so let's actually kind of think about it. Is this time invariant? And I would say no. Yes, it is time invariant. I would say so, yeah. Let's say you put in x of t minus tau, t minus t naught, then this would spit out negative infinity to t minus t naught of this, which is in fact quite literally equal to, if this is equal to y of t, this is just equal to y of t minus t naught. And so yeah, that should hold on. No, hold on. I messed up big time, sorry. Tau, there we go. Oh, I guess it is maybe not. I say tau is equal to, no, I say tau prime is equal to tau minus t naught. Then this is I think I can make a counter example. I just can't see particularly where I could think about it. I'll come back to this. Yeah, I'll come back to this because I would like to kind of make progress. It's already been an hour, so here, let me put a star on it. I'll come back to this right after. Maybe at the halfway point. Sorry about that. Sorry, this one took a little bit long. I'll try to speed through the rest. Suppose f of omega is the Fourier transform of f of t. What is the integral of that? Well, by Parseval's theorem, we know, or more formally known as Plancherel's, we know that this is equal to 1 over 2 pi integral of that. Hopefully this is hopefully there's no confusion in this in particular. And so all we need to do is just evaluate what this is. Well, this is 1 unit square 2 unit squares, 3 unit squares, so the area is just 6. Wait. I don't know if I'm absolutely tweaking. Okay. This would be we would consider the graph of absolute value, the magnitude of f of omega, which is oh my God, it's a little big. Let me fix that. Two, three, four. There we go. This is f squared. 4. So 1. Okay. Are there any questions? Oh yeah, this G d omega. Thank you. Are there any questions so far? So how I obtained this graph. Essentially what I did was all I did was take the absolute value and I squared each of the values at every single point. And all I need to do is find the area of this. Well, that's gonna be easy. It's just a sum of a bunch of squares. Yeah, not drawn to scale by the way, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1 over 2 pi times 10. And then now we just get 5 over 2 pi. Sorry, 5 over pi. Questions? For these partial questions, there's already operation. Since order operations gets tricky, it's always good to draw straight. Yeah, please just draw it out. Like, it's almost always better to just draw it out. Like, oh, it's a linear function here. If I square it, it must be quadratic. That's it. Suppose x of t is the input to an LTI system with an impulse response of sinc of 4t should be a signal that maybe you think of a rect function. And output is another rect function. X of omega is the Fourier transform of x of t, then what is x of 1? No. Okay. Okay. And so what we realize is that we have x of omega, and we put it into an LTI system with h of omega as the impulse response, frequency response, and we obtain y of omega such that this looks like this. Actually, maybe I'll just write it out as an equation. This should be, if I recall correctly, pi over 3 rect of omega over 6. And then this is pi over 4 rect of omega over 8. Wait, did I mess it up? No, I do not think so. No. Yeah, I'm fine. Okay. And so let's actually just graph it out. All I have is that do red, but blue. This is a big rect function that is of height pi over 4, but width 4, width 8, sorry. And then I have a purple function. It's a little taller. It lives right here. And so now okay, never mind. That's not a question. And so now for these questions, it's very important for you to see that hold on. Okay, this is that. Okay, this is that. So it's very important for you to see that you're thinking about x of omega multiplied by this rect function. x of y times this rect function is equal to this rect function. And from this point, actually, I don't even know why I color coded it since it's not going to be too important. And we observe that at 1, both of these points are positive. And so this means that at x equals 1, let's actually substitute everything. This goes to 1. Sorry, yeah. This rect function goes to 1. This rect function goes to 1. And so what we obtain is that x of 1 is just equal to x of 1 times pi over 4 is equal to pi over 3. And thus, x of 1 is equal to 4 over 3. And so it's kind of important to like observe where these rect functions are kind of like evaluated. Yeah. And so like it's just kind of important to like know when to substitute these values and when not to. I just drew it out for just for coherence. How does it go to 1? Okay. How does it go to 1? It's a rect function. And rect functions are literally rect functions of any like arbitrary variable, like say s. They are defined to be 1 if s is between -1 and 1, -1/2 and 1/2, and 0 else. And so this rect function goes to 1. Of course, this constant, I'm just saying this constant stays. Just the rect function goes to 1. All right, let me actually elaborate just this part. Okay. Balance my shot. No. Okay. Otherwise, next question. Let me just finish off all of this. What is, oh my, okay. Oh, well, you observe that this has a delta function. So this integral would be, let me actually reorganize it just for coherence. We have all this jargon here. And we have a delta function at -2. This means that all you need to do is evaluate this entire function. And in fact, -2 is inside -4 comma 1. And so you evaluate this delta function. Now you evaluate this at -2, which is equal to cosine of -2 pi. That should be 1 e to the -2 pi t, no, -2 pi j, it should be 1, and e to the -2 pi. And so what we obtain is that this goes to 1. This also goes to 1. And so all we have left is e to the 2 pi. Main chat. What happens if the -2 from the delta did not fit in the integral bounds? Then it would just be 0. Uh, no. Yeah. If the delta was not in the integral bounds, then you would just integrate over this. Because actually, no, it'd just be 0, yeah. Because what happens is that remember, this delta function is it's like a mass at this point and 0 everywhere else. And so if you're outside this, and let's say you're multiplying this red function with like a function like this, then the product will be equal to just 0 everywhere else except this point. And so now I'd be happy to tell you that if you take an integral between here and here, then it's just all 0. So you just be 0. Yeah. Anyways, next question. Rank all of it. Suppose x of omega is the Fourier transform of 2 rect t over 3. What is x of pi? This we have to use, or I would like to use just a Fourier transform pair that I like to use often and also proved in class. So it's good to have handy. I will not show it here because it's actually a very long, strenuous process. But essentially, this must mean that 2 rect of t over 3 has a Fourier transform of 6 sinc of omega, 3 omega over 2. And so now I evaluate this at pi. Then what this happens here is 6 sinc 6 sine of 3 pi over 2 over 3 pi over 2. This is equal to should be 4 times -1 over pi, which is -4 over pi. Voila. Okay. So this is just a Fourier transform pair question. It's good to have all these, like one of the common ones and kind of duly noted down. If S of t is an impulse train, okay, and note that this impulse train is kind of is like spaced out, and S of omega is the Fourier transform of S of t. What is that? Okay. So first of all, it's important to see that this is a translated Fourier transform, like as in the impulse train is translated by 1, I believe. So what does this look like? Well, it should be a sum of delta t minus 1 and then 2n. Okay? And so first of all, let me write out the time signal. I mean, sorry. The Fourier transform of this. This should be, sorry, it's 2n. Actually, at the end of the day, it's not gonna like really matter, but I want to show you the entire process and I'll kind of explain what I meant by it, quote unquote, it really doesn't matter. So the period is 2. This implies that the angular frequency must be pi. And so what this means is that the Fourier transform of this base signal, the untranslated version, would be pi sum of impulses spaced out by pi. All right, good start. So on and so forth, I'm sure. Very coherent. And what does this mean for the translated version? Well, what do we know about S of t? S of t, let's say this is equal to x of t. Then S of t is equal to x of t minus 1. And from our Fourier transform pairs, we know that x of t minus 1, given that this has a Fourier transform pair of S of omega, sorry, let me rephrase that. We have x of t minus 1 equal to x s of t, and we want to find the Fourier transform of s of t. Negative sign gets distributed to 2n as well. Oh, yeah. Regardless, it should remain the same though, but thank you for catching that. We know that x of t minus 1, x of t already has a transform that looks like this. This is x of omega. Then what this means is that s of t must have a transform that is equal to the modulated version of x of omega. I believe this is the correct version. And so why am I doing this? Well, this means that x of t minus 1 has a Fourier transform, or in general, x of t minus t naught has a Fourier transform of e to the negative j t naught. Sorry. Sorry, j omega t naught. Times x omega. This is a common property that we know. And I just applied it here to obtain xs of omega. And now all we need to do is just evaluate it. Oh, well, actually, no, we don't need to evaluate it. As in, this is now equal to a sum. And then we have these kinds of things in there. Hold on. Times delta of. But the reason why I said it doesn't matter is because now we're considering the absolute value, the integral over the absolute value. Is it squared? It is not squared. And well, we're taking the absolute value of pi e negative this times like all that, which may look annoying. D should be omega here, not t. D omega negative 127. But the only thing here is that, well, pi you could factor out. Yay. And this particular complex number, this is just like, how to put it? It's just one. Okay, let me actually elaborate on what I'm doing here. You could factor out the product of those two is equal to the product of this. So you could factor the magnitude out to two different terms as such. And you realize this is just one. No matter what. E to the j t naught is just one. T0 is one. Oh yeah, that's a good point. Thank you. I guess I could just be a little more coherent. But regardless of what t is chosen, despite what your delay is, it's essentially saying that the spectrum, the power of your signal will not change, which kind of makes sense. You know, like if I give you a system with X amount of power, and then I give you that same signal but shifted, the power should stay the same. And that's what we're exactly experiencing here, is that this modulation in frequency does not affect the power at all. Anywho, let's draw out my impulse train. I'm integrating from -1 to 7. And how many impulses fall in there? Well, I have one lying at each pi. And so I have one at pi and one at 2 pi, and that's it. That should be it. And so what happens is this is just a, wait, is there one more? There's 1 0. Oops. Boom. And then we realize that only three deltas fall in our area of integration. And so we get is just 3 pi. There we go. And thus we get 3 pi. Questions? Okay. Suppose f of t is equal to that, and okay, so we're given the Fourier coefficients. Okay. And okay. And f of t is that. And which of the following could be f of 1? So we have this is a Parsifal's theorem question, or from what I can see. And I know this because I'm given this particular integral. And this particular integral is always kind of nice to look at with respect to Parsifal's. Okay. And so one thing we do know is the following, is that if I take the average power or average square power of my time signal, take the average power of my time signal, then then this is equal to the sum of my Fourier coefficients. And then we realize that this sum of the Fourier coefficients is actually very easily defined. It's just magnitude of f of -1 squared plus the magnitude of f of 0 squared plus the magnitude of f of 1 squared. And these are about easy to evaluate. This is just 4. This is just 9 plus f1, which is equal to 13 plus f1. I'm going to make sure that I'm doing everything right. 3. Yeah. So basically, I basically just evaluated and expanded the sum of the Fourier coefficients just from what we're given. Oh, sorry. And now what we need to know is that this side is, well, omega naught is equal to 1. This implies that t is equal to 2 pi. And what this means is that this side is 1 over 2 pi of the integral over the period, and over any period. So we can actually take this particular period. Dt. And this must be equal to 28 pi over 2 pi, which is equal to 14. So we basically kind of track down the values of what each side would be in two different directions. And what this means is that f1 magnitude squared plus 13 must be equal to 14. And this implies that the magnitude squared of f1 must be equal to 1. This must mean that f1 magnitude must be equal to 1. And the only answer that suffices is negative j. And thus, f1 is a possible value for negative j. Okay? Part 4. Yes, question. Question? No more values of n. It was specified that only these values are like the Fourier series are literally just defined for f of n only for like it's explicitly defined that the Fourier series are only defined for those three numbers. I think Christopher, if you have your question, feel free to interrupt. Okay, never mind then. Okay.
Sorry, is it okay if you just go back for a quick second?
Oh yeah, of course.
Awesome, you're good. Thank you.
All right, of course. 13. Suppose f of t has a Fourier transform of a sum of rect functions. If g of omega is the Fourier transform of that, then what is g of pi? Oh, and so for this, I actually have this is also just a time, what do you call it? The time scaling property. If I recall correctly, if I have a function f of at, then the Fourier transform of this time scale portion is equal to 1 over absolute value of a, or 1 over absolute value of a. And then I multiply, and then I do 1 of f should be not just this. There we go. And so what we obtain is that this is just precisely for g of t in particular. This will have a Fourier g of omega is equal to 3 f of 3 omega. negative 3 omega. There we go. Because we have a equal to negative 1/3. Any questions just so far? How did I derive omega naught? Omega naught, I could directly determine from the period. Or, sorry. We always know that Fourier series will come in the form e to the jn omega naught. And so I could just deduce that omega naught is equal to 1. Okay. Otherwise, so now that I deduced the form of the g of omega, I could just evaluate it directly. This means that g of pi will be equal to 3f of negative 3 pi. And we realize that what is this? The things that we evaluated are 1 from 8.5 to 9.5, negative 8.5 to negative 9.5. And funnily enough, okay, I feel like I made a mistake here. 3g of 3 pi, 3 pi, negative. Actually, never mind, I didn't make a mistake. This is, well, 3 pi is actually approximately 9.42, which is definitely less than 9.5. And so this means that f of negative 3 pi, this 3 pi, negative 3 pi, falls into this region. And so this must mean that f of negative 3 pi, this is f, sorry. F of negative 3 pi must evaluate to a certain number, which is in particular 1. And so we just get 3. So this shows us that f of 3 pi is equal to 1. Because it falls into like where it's defined to be 1. That's the important part. That's 13. 14. What is the Fourier transform of that convolved with 1? Okay. That's very weird. Let's take a look. It's easy to be fooled, but please don't. Since it's convolved with 1, I'm just going to show you the convolution in time. Or I mean, now you can do two different things if you want. I'll do one method and you could do another. And here's one method. You basically do the convolution in time. Times 1. Then tau. Observe that we don't have the neg t minus tau section, where so how we determine that f of negative 1 was negative j. We know this because the magnitude of f1 must be j. I did the same process, was calculating the different answers, didn't want to assume as a j didn't say it was choice. Yeah, like every single answer choice, like we know that f1 must have a magnitude of 1. And so the answer must be negative j, because that's the only answer choice that has the, like, remember, it's which of the following could be f1. And so we have to choose the answer that satisfies the requirement. Yeah, so yeah. Awesome sauce, okay. So anyways, this particular question, problem 14, has 2 ways you could do it. I'm gonna do it one way, and I'll probably do it the other way as well. So evaluating this is actually very easy. Essentially what you do is you just evaluate this integral. It's from 0 to infinity for negative 4 tau d tau, because unit step function kills the bounds. Remember that the unit step function is 0. You know what? I'll actually write it out just for this one time, because it's nice to see it once or twice. Okay, we have this. And then what happens is that in this particular section, u of tau is 0 in tau between -infinity to 0. And that's exactly where you're integrating. And so, which is why this entire thing goes to 0. And then all we have left is the killed bounds. And this is what we see. We see this over and over again, how the unit step function kills the bounds of the integrals. It's very imperative that you see where and why and where this is coming from. Anyways, evaluating this integral is actually very easy. It should be just, what do you call it? Should be a constant that is 1/4. You could do the work, but it's just 1/4. And then now this is our time signal. This has a Fourier transform of 2 pi over 4 delta t, delta omega, which is equal to just pi over 2 omega. Okay, that's one method. The second method is to just take the Fourier transform. And so the Fourier transform of this convolution is equal to, this yields the Fourier transform e to the 4 plus j omega, and then you multiply just by delta of omega. And thus this is just equal to, whoa, hold on. This is 2 pi. 2 pi delta omega, there we go. And so now what do we want to find? Well, this, we're multiplying a delta function exactly with a function, and this is a delta function at 0. And so what this is this means that you're taking its 4 plus j of 0 at 2 pi delta of omega, which is equal to exactly the same answer. Not one particular method is better. It's just whichever one sticks with you. Because both clearly took the same around the same amount of time. Okay, next question. 15. Let f of t be the absolute value of cosine of t, and let f of n be the exponential form of the Fourier series coefficient for f of t. What is f of 0? Okay, so it's first of all important to see that f of t has period pi, not 2 pi. And that is because if you take the absolute value of cosine, it's going to look like this. This is pi, this is 2 pi. Normally, you would expect like something like this. But because you took the absolute value, we have a period that is actually just pi. And so now all it suffices to do is to find f of 0, which is absolute value of f of t, 1 over t, absolute value of, sorry, not absolute value, the integral over the period of f of t, e to d, negative j n omega naught t, but n equals 0. Let me actually just write it out. It's important to note that n equals 0, and thus what we obtain is that it's just 1 over pi, and then you integrate over, just take one arbitrary period. So let's probably just say negative pi over 2 to pi over 2 for cosine, the absolute value of cosine of pi, cosine t, absolute value, dt. And then remember, this just goes to 1 because the exponent is 0. And so now all we need to do is evaluate this. Well, In this interval, the absolute value of cosine of t is equal to just cosine of t because cosine of t is already positive. And so we could get rid of the absolute value function because we chose particular bounds where the function inside is already just a positive. So we could do this, and then we do this. It's the integral from negative pi over 2 to pi over 2, which is equal to 1 over pi of 1 minus negative 1, which is equal to 2 over pi. Voila. There we go. So again, this is a pretty straightforward question. It's just the most important part to see here is that the period actually changes because you take the absolute value of cosine. Otherwise, it's a very straightforward process where you just crunch out an integral. Number 16, if f of t is shown below, has Fourier transform f omega, then what is the Fourier transform of f of t when omega equals 1? Uh, oh, oh. Okay. This one really threw me off. Um, so this one you have to like read very carefully because this one like almost threw me off. It's very important to see that this is f of t where f is capital. So essentially what they did was f of t will yield some Fourier transform. We don't know what it looks like. Let's just say the Fourier transform looks like, I don't know. And then basically what you're doing is you're letting the Fourier transform spectrum look like specifically be our time function. And now we're trying to see what this yields us. So now we're doing the Fourier transform of so we take the Fourier transform of f of t to be our time signal, and then we're taking the Fourier transform of that again. That that is very weird. Okay. Let me actually think about this. Hold on. I believe that this would be something related to duality, but I don't think so. Okay. Let me try to evaluate this first. And so clearly, f of omega is equal to the integral from negative infinity to infinity for f of t e to the negative j omega t dt, sorry, j omega t dt. Okay? That's my, I'm just trying to figure this out because I've never seen this problem. Okay. And then what I'm trying to see here is I'm trying to take the Fourier transform of that again. So let's actually change this. If I take the Fourier transform of that again, then taking the integral again, infinity, at obviously at x w omega equals 1. And so, am I recording? Oh, I wasn't recording. Oops. Oh, that is a shame. I actually do it now. Oh, never mind, I am. Pause. Never mind. We're good. Take the integral again. F of t e to the negative j omega t dt. Maybe I want to change this to tau. And then e to the negative j t dt. That does not look very, very nice and promising. And then that should actually just be t. Okay. Well, Fourier transform the Fourier transform the t. Oh yeah, I forgot. That's actually one of the things that you learn in class. What was it? Um, yeah, great point. You have this kind of like relationship where f of t is equal to 2 pi f of negative omega. Yeah, this is why the cheat sheet's important, guys. That was real relevant. So given this, now you observe that the Fourier transform of f of t is just this, and now all you need to do is evaluate f of that, the Fourier transform of f of t at omega equals 1 is equal to that, which is equal to 2 pi times this point right here, 3/2, and thus is equal to 3 pi. Thank you. I kind of forgot that that is something that's on the cheat sheet. But yeah, so this is probably a very important thing to kind of keep in mind. Very neat property. And as you just keep on moving, we have until problem 18. So let's keep going. If y of t is equal to the convolution of x of t and h of t, drawn below, then what is the value of the signal of that when t equals negative 1/2? This looks like a time-shifting property in particular. And so recall that x of t minus t naught convolved, or maybe I'll use different ones. A of t minus t naught convolved with b of t, or maybe I'll even write out, given that a of t convolved with b of t is equal to c of t, we have this kind of nice relationship where the delays kind of cascade onto each other, onto the output signal. And so what we observe is that x of t plus 3 convolved with h of t minus 2, our output signal should be y of t plus 1. That is our output signal. And so now we want to evaluate this at t equals negative 1/2. Well, is y equals 1/2, and thus we just give ourselves this point. Is that clear to everyone? Okay. And 18. Suppose f of t is equal to that, and where f of n is in the given expression. If f of omega is the Fourier transform of f of t, then what is this? Okay, so here again, we want to kind of use the property of how we want to convert the Fourier series into the Fourier transform. And so let's do that one more time. Recall that f of omega given a specific Fourier transform is equal to 2 pi, the sum of fn delta of n omega naught. And we see that omega naught is equal to 2 here. And so we just take n minus 2, sorry, omega minus 2n. And furthermore, we realize that fn is only defined between -3 and 3. And so every other impulse function would go to 0. And furthermore, we can see that fn actually has an explicit definition. Perfect. And so now we have to think about when we take this integral, which delta functions fall into the 3-7 range. Well, we know that these delta functions are spaced out by 2. So wow, we have the one at 4 and one at 6. And the mass at this one is n equals 2, so it's 2 pi. Okay, well, I'll just say which one it is. So we have the one, we have the delta function at the n equals 2. So it's 2 pi times 2 e to the 2j, 2 pi j, plus, and then we have the one that n equals 3. Voila, e to the 3 pi j. So this is what we have. And mind you that we're integrating over this point. I don't know why I took that highlighter. And so now all we need to do is evaluate. We have 2 pi, and then we have 4. 2 pi j is just 1. So this is 1, and this is -1. And this is -8 times -1, which is equal to 24 pi. And hopefully that aligns with our answer. These questions? No. Okay, perfect. And I think that's halfway. So we're gonna take like a very like short fight. That's exactly halfway. So I'm gonna take it's just like a 5-minute break, like rest my eyes, go take a drink, and then we'll come back and congregate. So I'll be right back. All right, hello everyone, welcome back. So let's get right into it. Oh, and then okay, I have to go back to the question that I'd say I'll go back to. Where is it? Where is it? So for negative infinity, um, I got a comment saying that it is true that it is time invariant. And I do not doubt it. I think I could prove it algebraically. Um, the only issue is that like, do I, should I? Hold on, let me just think about this. Um, I don't know. It's kind of iffy. I guess that hmm. I don't know. I hate to say that this is. Hold on. Let me think about this. I want to compare it to this function right here. Then I don't think it's u sub compare. Hmm. So if it is truly linear time invariant, then what I would obtain is my true answer would be something that looks like this. Like this output, if ti, then my output would give me this. And I see, I see, I see. And after careful inspection, is it true? Yeah, it's true because we realize that this integral is the exact same as this integral right here. And by that, what I'm saying is that uh, if I give you any arbitrary function, and then I give you a time-shifted version of that arbitrary function, and then I tell you, oh, for the first one, I'm going to integrate up until this point, and then for the other function, like for example, let me actually do it in blue. So I shift this over by a factor. I shift my function over by a factor of t naught. And then I tell you that I'm integrating over a factor that is t naught. Um, the integral of the shifted function up until t. Uh, Actually, maybe I'll do the other direction. Is t minus t naught. I mean, okay, so sorry. And we're assuming t is positive here, but the negative case should follow as well. Um, or maybe I think it's better with just a graphic example. For this example, we have that we have a quadratic function, just an example. And then I'm integrating up until a certain t. Let's say t equals 1, whatever, just a t. In fact, let's make this equation red. Come on, give me a nice quadratic. And so that is integrating the shifted function by t. Okay. And of course, in this case, t is negative. T naught is negative. So I'm gonna have to do the same here. And then in this scenario, I have the same function, but shifted. This is by t naught. So so obviously I shifted it by t naught. And then I'm moving forward my integration by to t plus t naught. And it is realized that this integral, the integral, okay, obviously it goes to infinity. Maybe this wasn't such a good example. I will do a 0 and then up until, there we go. I think that's better. So clearly I moved where the 0 is. Essentially what I did was, despite having it shifted, as long as I shifted the the amount at which I shifted where I'm integrating also changed by this much. And because that's consistent, I basically shifted my function and shifted until I'm where I'm integrating by the same amount. And so what we get is that these two are exactly the same. And hence, letting a equal to negative infinity would maintain time invariance. So I'd be happy to elaborate, but this is disjoint from what we're doing right now. So yeah. Otherwise, thank you, Corey, for calling that out. You could just do it algebraically, apparently. So I wish I saw that earlier. But otherwise, we're just gonna keep on going forward from problem 19. And it's been 2 hours still. Let's try to pick it up. If x of t drawn below is the input to an LTA system with impulse response h of t, what is the output when y of t when t equals 1? You can do two different things here. And I will do one particular way because I like it better. So remember that our output y of t is equal to the integral from negative infinity to infinity for x of tau h of t minus tau d tau. This in particular means that when y t equals 1, we're taking the integral from x of tau h of 1 minus tau d tau. So now let's just draw out d h of 1 minus tau. H of 1 minus tau, we're reflecting, and basically what I like to do is I basically say I reflected. Let's draw the reflected signal. And then I move the center to 1. And so what does that mean? Hold on. Yeah. What color do I want? I'll just use blue again. Essentially, I move the center to tau equals 1. And so now I move the center to tau equals 1, and then I draw exactly what I have. And so now let's see what the value of each point is. Well, it's 0 over here, and then the height now is now 1. Then it was 1 times 0. And so I don't know if I want to draw it out. Maybe I just will. This is 1 multiplied by 0, the blue function. I'll just draw all the x's first. Like at each and every point in each and every region, it's two values multiplied by each other. In this region, it is the blue function is 2. In this region, the blue function is -1. In this region, the blue function is 2. And this region, the blue function is 0. Furthermore, in this region, the blue function is 2. In this region, the blue function is -1. In the red function. In this region, the red function is -1. And then this region, the red function is 0. And so now all we need to do is kind of consider all the points where at least one of them are non-zero. And so now this is equal to 4. This is equal to 1. This is equal to -2. And so what does this mean? This means that our resulting function should look something like this. It should be 0, 0, 0, 0, 0 all the way down. until -1, where it jumps to 4. 1, 2, 3, 4. And then the next point is just 1. And the next point is just -2. -2, -2. And then 0 all the way down. -2. And 0 all the way down. And so, find the area of this. Now, area, well, it's just 5 squares. And clearly I did something off here. Hold on. 0, 0, 0, when y equals 1. Did I do something off here? 4 times that. 2. Oh, this is not 2. This is 1. I don't know where I got that 2. Sorry. Typo. This is -1. So this should be. There you go. Sorry about that. This is 1 square, 1, 1, 1, 1, 1, and this is -1. And so we just get the area, which is equal to 4. And then we get 4. Questions?
Oh, can you go back up just a little bit, please?
Yeah, of course. Okay. Anyways, hopefully that was enough. X of t, next question. We have x of t equal to the convolution of e of 2 to the power of t, sorry, e to the power of 2t, convolved with u of t. Then what is x of 3? Just another pure convolution question, so we're just going to crank through it. X of 3 is equal to the convolution of, and from here, your choice of what you like integrate, like what you translate is up to you. And what I will do is I will do this, but of course, what you want to do is truly doesn't matter. I'll do u t minus, so 1, 3 minus tau. D tau. And so what is this? Well, we realize that u of 3t, oh sorry, u of 3 minus t is equal to 0 if tau is less than 3 and 1 else. And so what happens is that this integral bound kind of dies out just, sorry, greater than 3. And so this integral bound dies out so that we get 0, sorry, we get -infinity 3. Okay? And so given this, and now we just integrate over e to the 2t dt. And well, we know that this integral, this is just e to the 2e to the tau, and then we evaluate from -infinity to 3. And then all we need to do is note that, oh, sorry, this is 1/2. And then all we need to do is just plug it in. And then we're done. Voila. Nothing too shabby. If there's no questions, remember this is just a brute force convolution question. And so we're just gonna keep on going. For which values of A is sync of AT not band limited? So recall that sync of AT has a transform. The Fourier transform of sync of AT is equal to this. Rect of 2A. And this is always band limited for all finite A. And so we realize that all of these are not a nice answer, and so we get none of these. Not too bad. 22. Suppose rect x of omega is rect of omega over 2 and is the impotent LCA system with the frequent response of an impulse train. Oh, okay. And y of omega is the output. If y of t is the inverse Fourier transform of y of omega, what is y of 3? Okay. So it's important to note that we are basically taking y of omega to be x of omega times h of omega, where h of omega is an impulse train. And what does this mean? This basically tells us, but the issue here is that you're multiplying by it, you're not convolving by it. And so what we get is that the output is just x of omega times delta omega minus pi n. Huh? Oh. Huh. Maybe I don't want to think about this. I'll just leave it as this. Then we know that this has an inverse Fourier transform, which is equal to y of t. And we know that, how do I, I would like to do it like this. We know that this has an inverse Fourier transform, which is just x of t convolved with h of t. And now all we want to do is kind of retrace our steps. I don't know if we want to. If y of t is inverse Fourier transform with x of t. Okay. Perhaps this is not a wise decision. Hold on. Fourier transform. Maybe I'll try it this way. And maybe I could get something nice. Hold on. I'm gonna make it n. That's an impulse train. And what is y of 3? Yeah, I don't think that this would give us a nice answer. Hold on. Frequency response, that pi n. Not very satisfied with how this is looking. Okay. I lied, sorry. This is equal to? Okay. Yeah. We analyze what h of omega looks like, and it will just be an impulse train, right? And then x of omega is basically just a rect function from 1 to 1, negative 1 to 1. So and then we realize that every other rect function lies outside of it, other than this one. Oh, that's someone's starting to chat. Hold on. Let me see. Yeah. Okay. No, if it was infinity, that would mean the rect width and an infinite width to be yeah. Okay. Oh yeah, thank you. Yeah, thank you, Brian. But I just realized this. So essentially, when you multiply this, you realize that all you get left is just one particular delta function lying at 1. And so we get delta of omega. And recall that 1 has a Fourier transform of 2 pi delta omega. This directly means that 1 over 2 pi has a Fourier transform of delta. And so we can obtain our desired answer, which is 1 over 2 pi. Thank you. I don't know how I didn't see that immediately. It was just, I feel like it was pretty evident. But it is like possible to just kind of get tripped up on these kind of things. H of omega. Yeah, I'm only human after all. Anyways, next question. Infinity wasn't an option, it would not be band limited. Correct. Yeah. Suppose that when x of t is equal, wait, infinity over, yeah. Suppose that when x of t is equal to u of t minus 3 is the input to an LTI system with the impulse response h of t. What is h of t? Okay. So we see that y of t is equal to x of t, which is x of t convolved with h of t. And my first observation is that all of my answer choices are kind of just like in the form of deltas or unit step functions. And um, it's kind of weird to say, but you have to kind of notice that y of t is just a composition of unit step functions. So you have to realize that this y of t is just equal to u of t minus 2, sorry, plus 2, plus u of t plus 1 minus 2u of t minus 2. How do I get this? Well, you jump at -2, you jump at -1, and then you go down at t equals 2. Hence, you could just recover a y of t as a sum of unit step functions very, very easily. And then you realize that you are basically now trying to find the input-output relationship between this and a sum of translations of the input. And so what happens is that you can now deduce, given that output is sum of translated inputs we know that u of t, the translated inputs, we observe that we want to make sure to convolve u of t minus 3 with h of t such that we get each of these. Is this clear? Like, does everyone understand where I'm coming from when I say that I basically deduce that my output is a sum of translated inputs, and then I'm going to try to find my impulse response given my, I don't know how this turned into one, but I'm trying to craft my impulse response with respect to my output, with respect to my input. And so now the question is, I'm convolving this with something to be equal to this right now. And it kind of comes from like observation that your impulse response must be this particular combination. Let me make that a little more. Because now what happens is that if you combine these two, you get this. If you combine these two, you get this. And then what you do is when you combine these two, you get this. Should t minus 2 be t plus 2? Yes, there's, I don't know what is up with my computation today. Sorry about that. But yeah, essentially that's what's happening is that So it's important for you to see that h of t must be delta functions now. Because what we saw before, our observation that the output was the sum of translated inputs, we could use that fact to deduce that the impulse response must be a sum of delta functions. Is that clear? If there's no questions. And remember, I'd be happy to come back to these questions anyway, so I'm just happy to come back. But moving on, 24. F of omega is rect of omega, and g of omega is that. Then what is this? Okay. Um, so my first thought is that this is a signal. This, remember that f of t, g of t. Okay, first of all, maybe I want to write it like this. Let f of t times f of t, g of t be equal to h of t. Then we know that this particular integral squared is equal to 1 over 2 pi of h omega squared. That's a first start. And we also know that h of omega is equal to 1 over 2 pi of f omega convolved with g omega. And so now we could solve for f omega g omega. Well, the thing is that we're integrating over it anyway. So we don't really need to graph out what this looks like. We don't need to. We know that from the fact that g omega is impulse train, it's spaced out by a factor of 2, and which is bigger gap than rect of omega. This means that f omega convolved with g omega will yield 9 distinct rectangles, no overlap. Of course, this has a width 1, height 1. And so now, if I now try to integrate over this, well, this is equal to just 1 over 4 pi squared. I'm going to pull out the 2 pi. Oh my goodness, it's not 4 pi squared. It's actually 2 pi cubed because I'm squaring it again. And then it's the integral of this thing squared. But then you realize that this is just a bunch of squares that are spaced apart of height 1. So their height will not change. So, sorry, maybe I want to elaborate. Because the height is 1, sorry, the height is 1, we have that this will also be 9 distinct rectangles with width 1, height also 1. Okay? And so given this, because there's like just one square, which is just 1. And given this, now we could just integrate over this, which is just the easiest thing in the world. It's just 9 rectangles or 9 squares. Now it's just 9 over 2 pi 3. which is very easy. We didn't have to graph out anything. And this is kind of like the intuition that you want to kind of build up with, is that you just want to see like, oh, you could visualize it in your head. You're like, oh, it's just rect function convolved with delta functions. It must be a bunch of copies of rectangles. And then now all you need to do is just analyze the rectangles and where they're placed. But in this particular question, since you're taking the integral, you don't even need to think about graphing it. So, you know, that is
For
a nice question.
this question, I guess
Yeah.
like intuitively, initially I did like f of omega times g of omega and then the absolute value of that squared. But should we just be like really careful when dealing with multiplication between the time and frequency domain because of this special property where when you're multiplying in the time domain, it becomes a convolution in the frequency domain. And I guess like whenever we have questions like that, should we always just look out for that type of idea?
Um, okay, so there you have two questions there, or like maybe I feel like you had two questions there. For the first question, you elaborated on your thought process of
Yeah, which is
multiplying like when you're convolving these two, right?
yeah. Or at least I looked at Parsifal's theorem and then I immediately thought like f of t times g of t would be the integral from negative infinity to infinity of absolute value f of omega times g of omega
Yeah.
squared, which
Yeah,
is
and so
not.
you would consider, so your first thought was to consider the Fourier transform of this entire thing.
Yeah, yeah.
Yeah, and then that's how kind of like, that's how you want to proceed. And then given that you were given these two, you could deduce the Fourier transform of these by just taking the convolution. So yeah, that is basically how you want to think about it. Whenever you see this kind of integral, it's easy to assume participles, but sometimes it might literally just be like e to the like it might just be the Fourier transform of something at zero. So it's important to be careful, but it's only almost always just one of these two. It's just the Fourier transform of something at zero, which is easy to find the integral of, or you have to use participles. It goes either way. So I wouldn't stick with one particular method. It's just like keep your mind open, but keeping participle in the back of your head is a good idea.
Okay, thank you.
Yeah. But otherwise, just thinking graphically helps a lot in this class. Okay, so let's keep going at it. What is the period of f of t, which is that? Um, okay, so this is just one. That's the first thing that you need to know. And secondly, this has a period of 2 pi over 5, and this has a period of 2 pi over 3. And so, oh, Parseval, okay, it's called Plancherels. It's like the Fourier transform version of Parsevals, which is just this. Yeah, I just call it Parsevals just out of like habit, but it's technically not actually Parsevals. Um, by the way, for this particular question, we could see that this is just a constant, so this would really throw you off very easily, or even me. But after you realize that that's just a constant, you're just trying to take the period or the common period between these two. And so now you observe that you want to take, what do you call it? Basically take the ratio between these two. So you T1 divided by T2, and then what do you obtain? Well, I mean, you just find like, I don't know how to explain this like discreetly. Like when I look at these two periods, I'm just like, oh, the greatest common factor is just 2 pi. And so it's kind of rough. But let's say you don't want to do that. You want to find factors such that this holds. So m and n integers. And you want to find the smallest integers. And so you observe So just like, but mostly by inspection, kind of like doing pattern matching, you realize that it works out when m is equal to 5 and n is equal to 6. Um, I don't know. Like, if you tell me that one has period 2 pi over 5 and another one has period 2 pi over 3, I would just immediately think, oh yeah, both they would meet together at a common point, which is 2 pi. I don't know. It's kind of rough and tough to explain. Um, Another way to look at it is that I would just list out how shortcut to think of the exponential as a circle. Um, I mean that's the valid approach. I mean that's how I thought of it as well. But it's kind of rough because now you're considering the periods. And I guess what I would do is I would just list out time values where both of them are 0. And so I question myself, when is e to the 5jt equal to 0? Well, it's 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and then 2 pi. And then similarly, I list out for this, and then at some point, they will kind of meet together at 2 pi. And so I'm like, oh wait, we found out that at this time point, they meet together and meet the same value. Therefore, I just get 2 pi. I don't know. This common period thing between two different functions just comes from like visualizing how the function would look like and like maybe tracking down where they'll meet together. This is probably the most common technique where you just say, oh, they met together at 0, and then they met together at 2 pi. Therefore, the sum of those two must be like what do you call it? The sum of those two must have period 2 pi. Yeah, it's a little contrived, I would definitely say. But regardless, I'd be happy to discuss more techniques on how to like kind of come up with the common period between the sum of two functions. But for now, like this is once you get to this point, it's kind of up to you on deducing that 2 pi is like what works and the period between these two functions is that. I guess another way to do it is like the very it's very specific, but you just do the classic technique where you say, I want to find the smallest such capital T such that this holds. And then you realize that this is just this. And then now what you want is that you want T, you want to pick T such that e to the 5j capital T is equal to 1 and e to the 6jt is equal to 1. And thus you pick T equals 2 pi. That's it. So, and that's actually the smallest such T, which comes with like exposure. And so, yeah, and then you get the same answer. So there's many techniques to prove that if like to find the period of a sum of two functions, it's just that like you want to kind of figure out how to deduce that in the most intuitive way possible for each of you. I'd be happy to come back to this question actually, just because like there's so many ways to do it where you should find just a way that works most intuitively well with you. Anyways, 26. If x of t is cosine of t times cosine of 2t is an input to an LTI system with impulse response h of omega, where h is 1 between those two values and h is 0 otherwise, what is the output time signal? So this is a very classic like problem where we have a convolution between delta functions. We know that cosine of t is equal to delta pi at 1 plus pi delta at -1. Cosine of 2t is equal to pi delta at 2 plus pi delta at -2. And so this must mean that x of omega must be equal to 1 over 2 pi times the convolution of these two. Okay? And so now let's just evaluate this. Well, hopefully everyone remembers my delta convolution trick where you just treat it like polynomials. And so now I will solve this very quickly. We get pi squared delta at 3. Then we get, hold on, how do I do this? Plus, actually, let me factor out. I'm going to factor out all of the pi's first, so that's convenient. I don't write too many pi's. There we go. And now it's just delta functions, very convenient. Pi over 2. And it's this at 3 plus delta at 1 plus delta at -1 plus delta at -3. Perfect. And now what we want to do is, now we have h of omega that's sitting somewhere. So let's actually graph it out. We have delta functions that are sitting somewhat like this. And then we have h of omega that is sitting somewhat like this. 1.5 to 4. 1.5 to 4. That's 2, so there we go. And of course, this is 1. So now my question to you is, if I take the product between x omega and y, sorry, the output time signal will be equal to x omega times y of h of omega. And I want you to convince yourself that this is actually just pi over 2 times delta at 3 plus pi over 2 times delta at -3. And this is exactly because the frequency response kind of kills off. This is all 0, remember. So if you take the product of these two, then it would kill off all these impulses in the middle, and the only impulses that live are precisely the ones in these boundaries. And so this is -3, this is 3, this is 1, -1. And so we get this. And now what is this? Well, this has an inverse Fourier transform of 1/2. Well, actually, maybe I want to make this nicer. And then this looks very, very familiar. This is just equal to 1/2 cosine of 3t. And there's our answer. Nice. Questions? Okay. And we can keep moving. All right, 27. We have 10 more questions. Nice job, everyone. Keep it up. Consider the system shown below. For what values of A, there are a lot of these questions. For what values of A is the system linear and time invariant? Well, clearly not linear. Well, why is that? Well, I'll just give you the easiest counterexample. Like let A equal anything, then if bxt is given in, sorry, if xt given into the system gives me y of t, which is e to the xt plus a, then, I'm just wasting so much space. That's equal to y of t. Then if I give you bxt, then this gives me e to the b plus a. And clearly, this is not equal to b times e to the b times yt, though therefore not linear. If a equals x of what if a equals x of negative t? Then what do you do? A is a value. We're taking it as like a fixed number. A is like we're letting a be a fixed number. We're not letting a be a function. So a, like, we're fixing a. And so for any fixed number a, this will not be linear. That's what it means for, like, it means for what value. It means just a fixed number. And now let's check time invariance. Actually, it might be time invariant. Let x of t minus t naught be, like, if it were truly time invariant. Actually, let me just do this. If I check time invariance, I put an x of t minus t naught. I mean, just for practice, because, like, you know, since it's already not linear, we already have none of these. But let's just check time invariance just for practice. We input a time delayed signal, then what we obtain in the real world is x of t minus t naught. But then we realize that this is actually just equal to y of t minus t naught. So we have time invariance. But regardless, since it's not linear, we don't have that it's linear and time invariant. So we just get none of these. I'll choose such for, yeah. Okay, I see. What is the Laplace transform of that thing? Okay, so the very important part with these kinds of functions, especially the unit step function, is that when you scale it, you have to kind of deal with it in a way such that you can process it. And we know that u of t has a Laplace transform of 1 over s, I believe. Yeah. But this is clearly not in a way that we could, like, prep it up and digest it. And so it suffices to find what form this is in. Well, this is a function that is 0 for t greater than 6 over 2022 and 1, sorry, less than, and t greater than this number. And well, why can't we just change this into a form where this t, u of t minus 6 over 2022? These are the same function. Regardless of how you format it, this function will still look like this, where it jumps at 6 over 2022. And so what we can do is we could just now simplify this fraction. What is this? This is 1 over 337. And so now this will have a Fourier transform of, hold on. Yeah, this will have a Fourier transform. Remember that if f of t, sorry, if x of t has a Fourier transform x of s, then x of t minus t naught will have a Fourier transform of e to the negative t st naught xs. That's our property. And so what we obtain is that this is equal to e to the negative 1 over 337s divided by s. And so we get this answer. Okay? Sorry, my hand was hurting a little while I'm writing. But yeah, so this is actually, this is just something to keep an eye out for, is that unit step functions can be chopped up and like can be given to you in like a raw form where you can't really digest it. And so it's important for you to kind of see that, oh, no matter what constant you put up here, you could kind of simplify a unit step function to its most variable in form, such that you just have a naked t. So that's just important. Part 8, 29. What is the limit as t goes to infinity for e to the 45jt? So this is a conceptual question, and this is just none of these, because the limit just does not exist. Why is that? Well, again, you go back to the complex exponential example, where like it's just a spinning circle, and you're just like, you're just spinning. And let me actually draw that. That's a very nice circle too, but um position at t goes to infinity is indeterminate. Very important to see that. And so it's just none of these. Like that's just a thing about complex exponentials. Number 30. What is the inverse Laplace transform of that if x of s exists at the -3 plus 2j? And so by inspection, we observe that the poles must exist at s equals -2 and s equals 4. And so let's graph it out. And so we realize that x of s must exist at this point, which lives around right here. And so what does this mean? This means that our region of convergence must be to the left of both poles. And so this means that the system is anti-causal. And so this tells us that both are anti-causal. Okay? Now, given this, now we just need to find the anti-causal Fourier transform of both. Well, this now has inverse Fourier transform of, if I recall correctly, -3, or maybe I'll just write the base form first. S plus A will have has a Fourier transform pair of negative e to the -at u of -t. Please correct me if I'm wrong. Actually, check. Actually, it'll be convenient. Whatever. And otherwise, this must mean that 3 to the s plus 2 has an inverse Fourier transform of negative e to the -2t u of -t, and 2 plus s over -4 must have an inverse Fourier transform of 4t. There we go. Okay. And so now all we need to do, oh my God, I forgot the constants. And so what do we need to do? We just need to kind of factor out everything, combine these together, and we obtain -3 plus 2 u -t, and that's our answer. Voila. Nothing too shabby. Yeah, so this one also, like, it's important to like kind of keep note of where the region of convergence is in order to obtain the final answer. And yeah. 31. Suppose the inverse Laplace transform of that. Wait, I think x of t is inverse. Okay. And the Fourier transform of x of t exists. What is x of -pi? Okay. Hmm. So, oh, this one's cool. So again, I want to elaborate that for this, we deduce that the pole lies, oh, well, first of all, we need to identify A, and we want to put this in the form S minus S plus -2 minus J. So we put in the form, so now we got that A is equal to -2 minus J, and this means that our pole is at when S equals negative, no, 2. Yeah. Okay. So that's our first initial step. And so let's actually plot it. Let's plot our pole. And so the most important thing here is to realize that a Fourier transform of x of t exists. And this must mean that the Laplace transform must be defined on this axis. That's what it means for the Fourier transform to exist, is that Laplace exists at S when real part of S is equal to 0. Okay? And so now, what it suffices to do is to realize that you're now taking the Fourier transform where we're taking the anti-causal one again. And so this, from reference from above, should give us e to the, so well, this should give us -3 e to the negative at, so that's just 2 plus j, and then u of -t, anti-causal. Any questions? Okay, and so now that we deduced our time signal, we just need to deduce x of -pi, which is -3 e to the neg 2 pi e to the -pi j. That's not too fun. I think I missed out on something. I know I did not. E to d, yeah, I mean u pi. This is -3 e to the -2 pi. This is -1, and this is just 1, and so we get 3 over e to the 2 pi. Questions? Comments, concerns? It's easy, like I understand, like, even for me, like even as I'm doing that arithmetic, I got confused of like, oh, do I convert this to 1 or not? Just please keep an eye out for whether the exponent has j, because it's very easy to say, oh, that is 1, but it actually isn't, because the exponent is completely real. And so please keep a note and watch out for your j's. Anywho, moving on. So if x of t is sinc of 2022t, and h of t is sinc of 45t. If x of t is okay, if x of t cosine t is the input to an LTI system with impulse response of that, then what is the output? What in the world? Okay. Okay. So let's actually model this first. In reality, like first of all, we need to see that how do I want to put this? Let me think about this. See if there's an easy way to do it. Yeah. Trying to see what I can do here. Well, let's actually start with easy and kind of discover what x of t has a Fourier transform of. So we know that x of t has a Fourier transform of pi over 2022, and then it's a rect function of width 2022. Similarly with h of t, we have a rect function that looks like this. And over 90. So this is our initial setup. And now I'm considering doing the following operation. Convolved with h of t. Okay. And I would say this is not too, I'm just trying to think of a nice way to do it. Well, I will give you a statement and I will elaborate as much as possible if I can, but it's going to be very dependent on how you interpret the answer. So what I'm thinking is that let's try to consider the Fourier transform of this, because let's just consider the Fourier transform of this, or it's 45t. It's a really, really wide rectangle, and you're spacing it out by 45, I think 45. So it's a really, really wide rectangle. And even if I want to scale it, it's probably really hard. But I'm putting a copy right here. So a copy right here at omega equals 45. So I put a copy of x omega centered at omega equals 45 and negative 45. Where does x omega? And now just think about what that would look like. I just want to think about what that would look like. If I do that, then my resulting graph, please convince yourself, is that it would basically just look like this. Where in this area, it's 2 times whatever this initial height was. So if this height is currently pi over 2022, then the height over here would be pi over 1011. Oh my goodness gracious. Is that, oh, of course, okay, well, of course I have to consider the scaling factor. And so since we're doing 1/2 times x omega involved with sum of delta functions. Hold on. Okay, let me actually just write out the math because maybe that would be helpful. I'm doing my initial copy is x omega times, convolved with pi delta omega minus 45 plus pi omega plus 45. And then what happens is everything goes out, and then it's just x omega convolved with a bunch of delta functions. And we observe that because you're not spacing out the really wide rectangles large enough, they basically overlap in a very large section. And then you have to multiply by 1/2. So actually this peak right here is actually pi over. Remember, because you have 2 rectangles that overlap, but then you also multiply by 1/2. So this height stays the same because you're multiplying by 1/2. But regardless, I hope everyone's is seeing what I'm saying. I'd be happy to reiterate, but but this is the main idea of this entire proportion. And so now what happens here is now we basically deduced that the output is equal to all this multiplied by h of omega. If you want to see why, it's because I kind of omitted this part. It's kind of like we don't want to forget this last part where it's put into this LTI system. And so, and then maybe I want to highlight that this part is just this graph. So it's important to see where I'm like I'm trying to organize my work as well as possible, but I'm not doing the greatest. And afterwards, after I multiply by h of omega, what do we see? Oh man, what do we see? Let's see. So essentially what I'm doing is I'm what this rect function does is it kills off all the values, and what's left is just 1 pi over 2022 multiplied by just h of omega. Maybe I want to elaborate a little more on that. Let me just write it out. Um, so the reason why this happens is because, remember, rect is 1 if omega is between negative 45 and 45. But for omega between, but omega in that little range, let me just write this. We have this function. We have this function always to be pi over 2022. It's like this very small little range. And so what's happening is that everything else goes to 0. So everything outside 45 goes to 0. And what's left inside the 45s is precisely just a number, pi over 2022. So first of all, are there any questions regarding like how I went from this step to this step? This part is probably the most crucial part. And please feel free to interrupt if anything is convoluted. But essentially what we obtain is that this is just pi over 2022 times h of omega. And thus we obtain our final answer, which is pi over, so this has a Fourier transform of just pi over 2022 h of t. And so we obtain this answer. Any questions? I'd be very, very happy to discuss this part because multiplying rect functions can be challenging.
Yeah. For when we multiply x of t by cosine omega, like 45t, can we kind of just claim that the shift from the cosine omega naught t doesn't really affect the problem in this case? So we could just say like the transform of x of t cosine omega naught or 45t is about equal to the transform of x of t?
Yeah, precisely yes, because like they are basically the same within this overlapping region, which is almost everywhere. And what we're working with specifically this little sinc function, it makes it so that our initial translation was a little irrelevant.
Okay, thank you.
Yeah. Yeah, so that's good intuition. Like you can ignore it. Essentially, the entire point of what I was saying here is that you could ignore the fact that you multiply by cosine. It's just two shift. Yeah, it's just two shifted x of omegas, but they're overlapping in so many regions to the point where like you could kind of it's negligible. The fact that they're two shifted x omegas is negligible. Also remember there's a 1/2 factor, which is like important. So keep them on. Yeah. I got it saying pi over 45, not pi over 4. Yeah, not pi over 4. Did I write pi over 4 somewhere? Oh yeah, sorry, pi over 45. Thank you for the typo correction. Yeah. Anyways, good. That's a good question. That's a good question. It helps you visualize. Last question. Finally. Sorry, my neck hurts. Oh, my neck hurts a little. What is the phasor for this? So I'll be completely honest. Again, I'm not very good at I'm not very good at the sine cosine conversion. So, but but the normal trick is you basically take this argument, and what you do is you do 4 cosine of whatever you had before, and then you subtract pi over 2. Hold on. Hold my view. Yeah. Yeah. No, I don't think so. I think you... No, yeah, you subtract pi over 2, yeah. Okay. And so now that we have this, we just convert it directly into our phasor form. Well, after simplification, we have negative pi over 6, 3t. Okay. And then now we have 1. Is it minus pi over 2? Yeah, okay, yeah, thank you. Though, I'm sorry, but I always get confused. Okay, yeah, this is right. And then now this yields the phasor form e to the negative pi over 6j. This is very standard. There's multiple ways to check if your answer is correct. I always check just like using what I know, but it's important for you to build your own kind of methods to kind of make this little correction. I like this. I like this. Anyways, next question. We have 3 more, so keep it up, everyone. If x of t is the Laplace transform of x of s, which is that, what is the Laplace transform of x conjugate t evaluated at 2 plus j? Now, this is probably one of those. It's probably going to be all right. Okay. Oh, never mind. I don't think you learned a property about the Laplace transform of conjugates. So I think what you have to do, unless you did, and like please let me know. But otherwise, I think you have to just brute force and just solve for x of t. And so we realize that x of t, I mean, it's a little weird. We're not really given a region of convergence, but I guess I'll just work with it. Um, it's very weird. We know the known Fourier transform pair of the following. S plus A has a Fourier transform pair either that is causal, e to the negative at u of t, or we have the anti-causal, version. And so now we want to know what we are working with. Is it anti-causal? Well, we'll see. We'll see. It may even be that it doesn't really matter, but I think it may. For now, let's just go with the causal version. So I'm going to choose this, and let's proceed. So this means that x of t is equal to 2j e to the negative 3t u of t. That doesn't seem too right. And I do that, and I do that. Yeah, that doesn't seem too... Wait. Oh, never mind. I have to find the Laplace transform again. I'm sorry. Oh, okay. Huh. Then how would I proceed? Um, hmm. Oh, I see, I see, I see. So regardless of what you do, it looks like um it looks like because you're given x of s to be this, so let me show you what I'm trying to say. X of s is going to give you some real valued function, e to the something at ut times this, times this. Whether it is like causal or anti-causal. Maybe I want to like decompose it. So I will decompose this into x of s is equal to 2j times 1 over s plus 3, and which is equal to 2j, maybe I'll call it like, I don't know, y of s. And when we take the Laplace transform, this is going to yield us 2j y of t. But then y of t, we know for a fact will be some function, we know that, but it's a real valued. And so what this means is that if you consider the conjugate of x of t, we're basically taking the conjugate of 2j y of t, which is equal to just negative 2j y of t, because this is the only imaginary part. So all we need to do is like essentially what happens is that this in this entire part becomes imaginary, and when you conjugate this entire imaginary number, it just becomes a negative of itself. And so hence we get this. And so now, or yeah. And now, if we find the Laplace transform of this, regardless of whether this was causal or anti-causal, you don't even need to solve for it, because all you do is you just do the Laplace transform, and then you recover the Laplace transform of the conjugate of x in terms of whatever it was originally. And so, hold on. So yeah, so now this is equal to negative 2j over s plus 3. Well, what a nice question. That was actually pretty cool. And then you take, this is, yeah. And then you take it at s equal to 2 plus j. And then this leads to negative 2j over j plus 5. Voila. That was an interesting question. I kind of liked it. So it didn't matter which one you chose, but the moment you choose one, you'll kind of waste more time. And so it's important for you to see that the inverse Laplace transform of this function was a purely imaginary. Let me actually label that. Thus, the entire point is purely imaginary. And so when you conjugate it, you're just taking the negative of it, because that's what you do with imaginary numbers. You just take the negative of the imaginary part. And since it's purely imaginary, when you take a conjugate of a purely imaginary number, you just take the negative. And so hence you get this. Wouldn't the anti-causal case have been a negative sign? No, because I never pulled out or pushed in any negative numbers. All I did was I just kept my time signal, like the inverse Laplace transform of y of s, to just be y of t. And so I did no exchange, like whether it was causal or anti-causal, it was all contained within this y of t. No minuses coming out or no minuses going in. And so it's kind of like a net, like it's a net zero. I never pushed in any negatives. I never pulled out any negative signs, so we don't need to care about it. So we don't need to conjugate s when we sub it in. No, because we're conjugating in the time domain. Since we're conjugating the time domain, you don't need to do any conjugating in the s domain. It doesn't count as covered instance. If it's covered in the conjugation property. Apparently, the conjugation property was covered in Spencer's videos. I don't think if the professor did not cover it in lecture or any of the discussion notes or like the post-lecture follow-ups, then it will not be covered on the exam. As you can see, like I did not use any like properties. I just followed along just Fourier transform, like Laplace transform things that we learned in class. I didn't particularly use anything contrived. Anyhow, that's 34. Interesting question. 35. Suppose f of t is periodic and can be written as shown below. Let me actually organize that. So when you see these kinds of sums, it's important for you to just kind of organize it in a way that it's nice to see. So let me just do that. So we can clearly see that omega naught is equal to 3 over 2. And this means that t is equal to 3 pi, 3 pi. Yeah. No. No, 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 no. Hold on. Am I just, what am I doing here? I think it's 3 pi, 2 pi over t equals omega naught. Wait, why is this tripping me up? Sorry. 2 pi over t equals 2 pi over t equals omega naught. So 2 pi over, yeah, sorry, it's 4 pi over 3. Sorry about that. Yeah, thank you. Yeah, sorry about that. And if f of t is the input to an LTA system with frequency response h of omega, what is the output y of t? Okay, well, this is, thank God they gave us a graph because I would not want to graph out another one of these. But we realized that f of t is a periodic function with Fourier series given. And so we could yield the Fourier transform to be 2 pi times the sum of the Fourier coefficients times a bunch of delta functions spaced out by omega naught. So I guess this period was not actually very important. Okay? And so now let's actually draw it out. Well, we have, draw it in blue. We have a delta function in the middle, delta function at 3 over 2, negative 3 over 2, delta function at 3, and then so on and so forth. But then you realize that all deltas go to 0, except for, which ones is it? It's equals n equals negative 1, 0, and 1. So what we have left is that f omega h omega will be left with the 2 pi times 1 over 3 delta of omega plus 3 over 2 plus the 0 case, which is 1/2, is it 1/2? 1/2 delta of omega. And then the last case, which is same, 1/3 delta of minus 3. And so what do we obtain? Well, f of omega times h of omega is now 2 pi over 3 delta of omega plus 3 over 2 plus 2 pi over 3 delta of omega plus 3 over 2 plus 1/2, sorry, pi of this. Hopefully I didn't miss anything. Yeah, hopefully I didn't miss anything. I think I definitely missed something here. Hold on. 2n squared. Yeah, that's good. Oh, maybe not. Maybe not yet. Good question. What is the general property of connecting exponential to the delta? Um, oh, like if you're talking about in the sense of this, basically we have that if f of t is equal to has the Fourier series decomposition of the following, then this has a Fourier transform of 2 pi of fn delta omega minus omega and omega naught. This is the property that we have, where you're converting the Fourier series into the Fourier transform. Anyhow, I definitely got something off here. I'm missing a 2, and I'm trying to find where. Let's see. Equals 0, equals 0. That is weird. Oh, I see, I see. I forgot. Um, I forgot to multiply by h omega at all these points. So this is h of 3 over 2, h of 0, and I multiply h of 3 over 2. Yeah, there we go. Okay, that looks a lot better. That's 2 times that. And at these points, you multiply by this. It's 2. This is 1, 1. And so what we have left is 2/3 times omega pi delta 3 delta pi omega minus 3. That should be a minus. And then plus 2 pi delta omega. And so now this is a known Fourier transform. This is 2/3 cosine of 3 pi over 3 over 2t. And then this has a Fourier transform of just 1. So this is our final answer. How come you think I multiplied by h of omega. Okay. All right, last question. What is the Fourier transform of e to the -5 absolute value of t minus t when omega equals 2? I genuinely do not think that there is a cheat way to do this. This is just, you just got to do it. Let me think though. Yeah, you just got to do it. That is not very fun. Yeah, you just got to do it. So let's just, it's just nice algebra practice. So we know we want to take the following. It's integral of e to the -5 absolute value of t minus t, e to the -j 2jt dt. And I want to write that over everywhere. And now remember that we have to split this into 2. So we have to split this into 2 integrals from -infinity to 0. And this is when we take what do you call it? We take -t. And so this would be 5t minus t minus 2jt dt plus integral from e to the -5t minus t minus 2jt dt. And so what we do is, oh, and this is actually not that bad because this is just a nice 4 2 minus jt dt plus integral from 0 to infinity for e to the -6 plus 2j t dt. And so now this integral shouldn't be too bad. We just have 1 over 4 to j, 4 to j, and then let me think. And then we have the thing outside, -infinity 0 plus 1 over -6, -2. And then we have the integral evaluated from 0 to infinity. And so this is just 1. So we have that left over. Let's subtract. Let's just keep adding. We have that, and then that is just -1. Oh, that's convenient. Then the negatives cancel out, and so now we have a nice sum of complex numbers. Hooray! And now we just need to add these two complex numbers. So fun. This will be 6 plus 2j plus 4 minus 2j divided by the product of the two. It's 24 plus 2 minus 12j plus 8j, which is equal to 10 over 24 minus 4j, which is equal to 5 over 12 minus 2j. And I'm off by a factor of, oh, that's a 4. There we go. Splendid. And that's our answer. All right. Oh, I need to add, I missed something. Or no, actually, that is the same answer. I just need to take the negative sign. Yay. Okay, and now we get the final answer. Okay. All right. That concludes the final. Thank you for staying. I would be happy to take any questions if there are any, and questions will be recorded so that everyone could benefit. Questions? I'd be happy to go back to any questions. And I have all night, so please let me know.
For problem 36,
Mm-hmm.
I was trying to use the property that e to the negative a times absolute value of t is a Fourier transform of 2a over omega squared plus a squared. And then I was trying to combine that with the shifting property, but for some reason it didn't work, and I was trying to understand why.
I don't think that you should like the main reason why that won't work is because of this. It's because of this.
Hmm.
That just kind of ruins everything. So I don't think it would work at
Yeah, it didn't work. I tried to
at all,
solve it.
no. Yeah, it's
Okay.
very unfortunate. Yeah, I don't think it will just work at all.
Okay. Thank you.
Yeah, so this is just a brute force question. Yeah, any questions? I'll just stick around until no one has questions. So, please feel free to comment. Would you be able to go over 24 again? Yes, sure. Okay. So this one kind of relies on like this. If like making this substitution will help a significant amount. So after you make this kind of like just like you just name it, you could make this kind of equality right here. And please let me know what like just send a chat message whenever like something is unclear, and I'd be happy to elaborate more on that. But I'm just gonna like kind of narrate more on specific portions. And so up until this point, it's just like kind of renaming stuff and kind of trying to elaborate. And I'm assuming that the confusion comes from when we are trying to find out what this is. And so maybe if I drew it out, that would be kind of okay. So I would actually just draw it out. We know that g of omega is that. And what is that? That's just 9 delta functions. Okay? And then what is f of omega? F of omega is a rect function. So therefore, if you're doing this convolution, then what happens, I'm just doing a rect function, and it suffices, and I showed here that the impulse functions are actually spaced out more than the rect functions. And so all I do is I just do this. When I convolve the two functions together, this is what I would get. This is exactly what I meant by there are 9 distinct rectangles with no overlap, with width 1 and height 1. Or, yeah. And remember, I factored out the 2 pi. Remember, because when I evaluated this, I pulled out all the 2 pi's to the outside so that I only need to deal with this. And then now when I'm dealing with my f omega convolved with g omega, I understand that it's just a bunch of copies of f omega, which is just a rectangle. Anything unclear? Or would you like me to elaborate something again? Which property did you for the initial equality? This one? Yeah. That's just like, what do you call it? It's like the Fourier transform version of it's like the Fourier transform version of Parsifals, where you have like the square of the magnitude of the energy is equal to the square like 2 pi, like 1 over 2 pi, and then the square of the magnitude of the Fourier transform. I thought Parseval was only over a period. As I said, like you have Parsifals, which is this. And then and then we remember we use this multiple times. If like my square magnitude over the integral, this is equal to the 1 over 2 pi square magnitude of the Fourier transform. Like when I say Parsifals for like Fourier transform, this is exactly what I mean. Because it's a parallel, right? Shoot. Uh, Yeah, no problem. Um, questions, any questions? Just wondering if there's no quiz. Will there be a review session tomorrow? I actually have no idea. I should probably ask Philip. Um, I don't think so, but I don't think so, no. But I think it will be helpful to ask because the Zoom is up there for some reason, but yeah. Let's see. Um, all right. I'm just gonna keep sticking around until people leave, but yeah. Also, cheat sheet doesn't have to be written or can be printed stuff. There's no limitation. You may print stuff, you may write it on an iPad and print it, you may make your thing like microscopic as long as it is a 8.5 by 11 paper, A4 paper, 8.5 by 11. Questions? Yep. All right. Well, I'm just gonna stick around for maybe like another minute if you have another question. But all right. Thank you for coming. All right. Thank you.